Okay, so first of all, I would like to thank the organizer for giving me the opportunity of presenting this work in this very nice conference. So, um, I think that the problem posed by Serre in the last 50s of characterizing the fundamental groups of complex algebraic manifolds among finitely presentable groups. This problem is not probably not going to be solved in the next few years, even in the most constrained case of complex projective manifolds that is somehow very constrained. So I will not talk on the general Serre problem, but just on the part that concerns compact objects, so complex projective manifolds. In fact, the restrictions we know, like very elementarily, every finite index subgroup of the fundamental group of a complex projective manifold. So every finite index subgroup has even rank by basic Hodge theory. So this kind of restrictions also apply to fundamental group of compact Kähler manifolds. In fact, all the restrictions we know about the fundamental group of complex projective manifolds, all these restrictions also apply to fundamental groups of compact Kähler manifold, which is a more general and more analytic setting. These restrictions come from two sources. So the first kind of source is tree actions or Hilbert representation of the fundamental group with non-zero reduced first cohomology. And then it's Gromov's non-splitting theorem and its descendants as explained in Donuora-Pura's talk and also in Thomas' previous talk. And finite dimensional linear representation of the fundamental group of when its Kähler group behave in a rather special manner. And these are the source of known restrictions. So this is my excuse to fix the following setup. So X will be a compact Kähler manifold. I'm not precise, so it's connected. I'm not precise on the dimension. And of course, I make the hypothesis that pi1 of X is infinite. Well, it was proved by Serre when he formulated the problem that every finite group occurs as a fundamental group of a complex projective manifold. So the Serre problem is really interesting only in that setting. And I will fix a normal subgroup of the fundamental group. And soon, H will be the kernel of ρ, where ρ is a complex linear representation of the fundamental group of some rank with infinite image. So we have to. So if we want to control this object geometrically, the important object was introduced by Kolar and Campana, and it's the Shafarevich variety of rho, and we want to give some structural theorem of this object. But before giving this structural theorem, I should make some preliminary remarks and definition. So the first remark is that phi1 of x is a bimeromorphic invariant, and that in particular, when we have a meromorphic mapping of compact Kähler manifolds, let's call it F, we have an induced mapping at the level of the fundamental group, induced morphism. Okay, so the first definition is actually a theorem. So, theorem definition. So the theorem is due to Campana and Kolar independently around 93. Well, Kolar treated only the projective case, but the same kind of argument works. And so our setup is that X is a compact Kähler manifold, and then there exists a certain map. Let's call it G of H. It depends on the normal subgroup of pi1 of X to a certain compact Kähler manifold. So it's a meromorphic connected with connected generic fiber. A fibration of compact Kähler manifolds, which is almost holomorphic, which means that the indeterminacy locus is not mapped onto the target, and unique up to bimeromorphic equivalence, such that the following condition star is satisfied. So if Z is a normal, irreducible, compact, complex analytic space, so we need normality. Over x, so and f z2x is holomorphic. And which passes through a very general point in fact, here one can be more precise. We know that X, since it's a compact Kähler manifold, has a Barley space. And the Barley space comes with natural incidence correspondence. And the various the image of the incidence correspondence inside X is a C-analytic, a closed C-analytic set. And okay, so some of them are not equal to X, and very general means outside of this countable union of complex analytic subsets. So if Z is such an object, so in particular, it completely, it certainly avoids the indeterminate C locus, I think. The composite of G of H with S is a constant. If and only if the map induced by F into the H quotient of the fundamental group, so the composed map, let's call this quotient rho, as finite image. So H is a certain normal subgroup. So there is a quotient. Okay, so that's well formed. And certainly, in some sense, this is related to the Shafarevich conjecture that was discussed before by Mohan, and it has, so in the case of H, the trivial subgroup, this fibration kind of is a trace of the proper map from the universal covering to this Cartan-Reimert reduction, so the famous Stein space. So, but I don't want to go more into these details, except that I will call, so that this is just terminology, GH the Shafarevich map, the Shafarevich map. I need a second definition, which is not, unfortunately, a theorem, which is actually a more precise way of, which defines a more precise model of this Shafarevich, H. Shafarevich morphism. So a model which we like call a sh of H. Of GH. So where this guy is a normal compact complex space, is a Shafarevich morphism if, well, the condition star holds, but with a small modification. Star has to hold with modification, and with the following modification. Z should be promoted to be a compact C-analytic connected space. And no restriction on its image. So no very Z can take values in the very special points. Okay, so it's for all of them. So no, not normal, not normal. You really need, you know, it would not be enough. In fact, this famous what we call the Norrie chains, so the things like that that could open up like that. No. It's a true morphism. So it's a regular model. It's not a birational here. It's really so that's a model is a holomorphic thing that contracts exactly those compact connected subspaces that have finite pi1 image. Okay. So it's, of course, so. I think so, yes. So, so here arbitrary singularities are allowed, and there is no general theorem for the existence. Yes, exactly. It's exactly this condition, but with with a small. Okay, so no very general point. Of course, things, funny things could happen at at special points, and the existence of such a Shafarevich morphism excludes this strange behavior at special points also, and there is also this. We have to allow you know, even reductible stuff so that to exclude these Norrie chains that could open. Of course, there is no counterexample to the existence of this object, but let me nevertheless make some remarks. So first of all, it is uniquely determined. Well, in fact, we have a complete characterization of these guys who are contracted when it exists. Okay, so it's the Shafarevich morphism. And we will also, in the case where H is the kernel of a representation, use abbreviation like that. And similarly, what happens? It could. Yes. So if you replace x by something birational, this guy, the map, that's certainly a very okay. The model is exactly the same. So the model is exactly the same. It's I will give examples so that, and so the model is completely birationally invariant. So okay, no, that's but the well, the Shafarevich conjecture and this question are actually birational invariant. Okay, so if that's a very good point. Okay. Let me give some examples. That will be immediately familiar to people. So let me give two examples. First of all, assume that the normal subgroup is the group of commutators. Then it is a very nice exercise to show that if we look at the Albanese morphism of X to the Albanese torus, and we do the Stein factorization, it will be finite here, and here it will be a connected fibration to, let's call it Y. No, it's the Stein factorization. It's not the image. It's so it's finite over the image. Okay. So if we give this Stein factorization of the Albanese morphism is nothing but the Shafarevich morphism for this H. Let us give a second example, which is very much, which has very much this flavor. Let us assume that now rho is what is a monodromy of Z variation of Hodge structure, of course polarized, over the compact Keller manifold X. So that's a bit of an academic example, since it's rather difficult to construct, but okay, there are nice examples. Yes?
The Albanese mapping depends on the chosen best point.
Yes, yes, but you know, it depends. Just depends by a translation, and you know. So the Albanese mapping is in fact not uniquely defined. Of course, you must say, okay, I map this guy to one of these points, but the various incarnation of the Albanese morphism are just obtained by post-translating. Oh, but the Stein factorization, the fibers here, the guys here who are contracted by the Albanese morphism, these guys are completely the same. It does not depend on, so the translation does not, will not change anything. Yes, 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 yes. Yes, yes. It's so the morphism. Yes, yes.
If you go to the covering, you got to usually quotient by age.
Yes, yes.
The problem after you complex Euclidean space.
That's right. That's right. That's right. That's right. And this what Mohan tells you is a proof of the fact that the covering space the universal abelian covering space is holomorphically convex. Okay. Yes, yes, yes. And so if we have the monodromy of a Z variation of a structure, then we have a similar construction of period mapping to, so this will be the image divided by, which acts on this Griffiths period domain, and so let's call it P, and we have the Stein factorization here, and the Stein factorization of P is nothing but the Shafarevich morphism of ρ. So okay, here are two examples of these notions, and I can state the first theorem of this lecture. So theorem 1. Of which a huge amount is due to Zuo, and some small precisions are due to Campana, Clodon, and myself. So it was posted in 2 years ago. And okay, X is a compact Kähler manifold, ρ is a representation, and we assume that the Zariski closure in GLNC of the monodromy group, we assume that it is semi-simple. Then no, the usual definition of semi-simple representation, and that's is when this is a reductive group. I don't know. Well, at least this is the way it is used in the paper of Ramachandran and Lazel. In that case, I prefer to use reductive, but here it's semi-simple in the Zariski closure, so it's stronger. Then the Rho-Shafarevich morphism exists. Good. So Zuo did essentially constructed this and proved some more properties, some factorization property that I will explain above. So that's the slight, the slight improvement. And if we have an étale covering, finite étale covering, such that the image by rho of pi 1 of x prime, which is a subgroup of the general linear group over C, such that this guy is torsion free, then the Shafarevich variety of x prime corresponding to rho, let's call it E star of rho, is of general type. And there exists a factorization let's put some hat here. To G and C, so that the pullback of rho to x prime factorizes through the Shafarevich morphism. Okay, so hat means, thank you, hat means a desingularization. No, it has so it's a regular model of this guy. Oh yes, but what the? Yes. Okay. So this is okay. To be of general type is indeed a statement over the desingularization. Okay, and so thank you, Claire. That's right. To be of general type means that a smooth model is of general type. Okay, thank you. Yes. Of course, if you have an abelian variety. Okay, and certainly abelian varieties plays an important role in that kind of statement. So before giving 2 words on the ingredients of the proof, I would like to make a small remark. Okay. That's there's so of course by the existence and the unicity of the fact that it is well defined, it is functorial, and there is a finite morphism from this guy to the Shafarevich variety. So that's that's a remark. It's No, come on. The torsion here You know, for instance, the Shafarevich variety can be P1. Okay, in very simple example, and it can be P1. So yes, so okay, it is P1. If one use the true structure of the Shafarevich variety, which is not to be a variety, but a stack, with the singular points and okay. If you use the structure of a Deligne-Mumford stack, actually it's not necessarily an orbifold because okay, generic isotropy may occur. Then if you have this extra structure, but I don't want to talk about that because I would say stupid things, I'm sure. Yes. So it would be étal if you put the correct stack structure, but here it's just finite. Is so a morphism is a finite morphism. Okay. So I won't explain the proof, but the ingredients come from Zuo, of course, plus this paper of mine that Mohan had cited, 2004, plus two interesting ingredients. So first of all, it's a slight generalization of a classical result of Kolar, which was pushed to the Keller case by Nakayama, Noboru Nakayama, with a slight twist. So if x f to y is what? Connected vibration of compact Keller manifolds, then we have the additivity of Kodaira dimension if the general fiber has general type but so the classical eta k will be with k of y, but here it's something slightly refined, and we really need this refinement where this is Campana's orbifold base. So this has to deal with multiple fibers of good models of this one, and you take the infimum and not the GCD of the multiplicity, but it's really the infimum and Campana's strange definition that occurs. So that's the first ingredient, and the second ingredient is of course Ueno's theorem on subvarieties of complex tori. In fact, it's more a variant due to Kawamata, so that when we have a variety which is finite over a complex torus, then it's Itaka fibration. So the map corresponding to pluricanonical forms. So this Itaka fibration is base point free. And so there is this abundant statement. And it's also a torsor over a general type basis with fiber with a torsor over a complex torus, which is an isogenous to a subtorus of the complex torus. So it's about the structure of the Kodaira map of varieties finite over complex tori. And I will come back to this later. Okay, let us give a corollary, which is about the case when this is reductive, and it will be so. Basically, if we have a reductive group, the way I understand it is okay. R reductive is something like a product of a torus times a semi-simple. It's not completely correct, so we have to give a slightly technical statement. And for future reference, I will try and put it correctly. Yes? Do I need characteristic 0 or not? I must say that I did not think about that. So if I try to... Okay, so you tell me it does not depend on... Okay. I did not think about that, and it's better that I make no statement. So, it could be an infinite representation in, say, some function field or something like that. Okay, I don't want to make any statement about that, because it would be wrong. No, it has, okay. But so let's look at that, the case where this guy is just reductive. Then, okay, this is the statement that we got with Campana-Clodon. Then, if we choose an étal covering, such that this guy is connected, this is torsion free, this image is torsion free, and we defined a morphism from this G to its modification into a product of a semi-simple group and of a torus. Then this guy factors through a representation sigma of the product of this general type variety times the Albanese. So it's a product of a general type variety by a complex torus inside G, L, and C. Well, it's certainly a trivial corollary, but I have to state it because I will need it in the slightly less sketchy proof of the theorem I know will so that's the second theorem, and this is due to always these people. So no hypothesis on this Zariski closure. Unfortunately, we did not quite, we did not succeed in proving the existence of the Shafarevich morphism here, but we have something which is even better in some sense. Then there exists, it's not so easy to control, an étal covering of X such that the Shafarevich variety of X prime, which is the finite modification of the Shafarevich variety of X, as we had explained, is bimeromorphic to a smooth fibration, so no singular fibers. So certainly it will be on some model, and I choose a convenient model because this is just defined up to bimeromorphic equivalence. Such that this is of general type, and the smooth fiber are complex tori. An even more precise way of stating this theorem is to say that this guy is nothing but the Itaka fibration. So this Shafarevich variety has this property, and also I forget an important addendum, and the original representation rho factors through this Shafarevich variety, which means that the representation factors through the fundamental group. So we have, this is certainly true by what is explained here in this special case, but in order to give a rapid sketch, so it will be a sketchy sketch. So the step one is what happens in the orthogonal case, what happens if the fundamental group has a unipotent and this was studied by Ludmil Katsarkov in '93, and essentially one obtains this because then really the Shafarevich morphism of exists, and is the Stein factorization, still a Stein factorization, of an adequate quotient of the Albanese torus. So this is okay. I don't want to explain that. And since I don't have a lot of time, I will be very sketchy about step 2. And I will just say that it is a relativization of Katsarkov argument. This relativization of Katsarkov argument will give us the fact that we have fibration, that the Itaka fibration of the Shafarevich variety is a fibration whose general fiber is a complex torus. Okay, so that's essentially step 2, and step 3 is the smoothness. But here we basically just have to apply the corresponding result of Kolar, and also in the generalization by Nakayama to the Keller case. So, so we have this general result. So, okay. So the Shafarevich variety. So the control of the structure of the Shafarevich variety is good because somehow the Shafarevich variety controls the part of the kernel of Rho that is constructed out of complex objects, I would say. So that's. But I would like to give some more applications of this theorem. So and I will give the first application, which will be theorem 3 of this lecture. So 1 year later. So same setting of a representation of a Keller group. Then there exists X prime, a complex. So we start with X, compact Keller manifold, and Rho, a representation. Then there exists a complex projective manifold. There exists rho prime, a representation in the same group of its fundamental group such that the monodromy groups are commensurable. More precisely, the image of the complex projective group is inside this. Besides, furthermore, if rho is faithful, then rho prime can be chosen to be faithful. No, it's just any representation, whatever the Zariski density. The corollary of this statement is that am I right? I just have 5 minutes. Yes? Okay. So the corollary is that if a Keller group is linear, so a linear Keller group has a subgroup of finite index which is complex projective. So this is a result in the direction of the Keller versus projective problem, which is a certain instance of the Serre problem. Is the fundamental group of a compact Keller manifold always the fundamental group of a complex projective manifold? And this is absolutely non-trivial because of Claire's result that Kodaira's conjecture is completely false and that there exist non-Keller, there exist non-complex projective Keller homotopy types. Actually, 2 homotopy types. So that's the best. But anyway, so I will just wave hands for this theorem. So essentially, we have to construct such a complex projective manifold X prime, and what we start with is this smooth complex torus fibration, which is scalar. Then, of course, if the base here is a point, we have a compact complex torus, and we all know that it's easy to deform it to an abelian variety. So it's easy, but there is some Hodge theory to be done, but it's relatively simple. So the new projective variety X prime will be constructed out of this guy. So first of all, what we do is that after an étale covering, so that's also a sketch. After an étale covering, the degeneration of le ray spectral sequence permits to construct a continuous section to this vibration. And all this will be Keller. So we are reduced to the case where this smooth vibration actually has a section. And so it's a Jacobian, so it's a relative Albanese morphism, the relative Albanese morphism of that guy. When this is done, then what one basically do is that in that case one proves by a very simple deformation theoretic argument that we can deform such a Keller vibration in complex tori with a section to a vibration hollows with the section, hollows whose fibers are abelian varieties. So it's a deformation argument with a rather simple Hodge theory, and basically we use some notes of Claire to sort out this thing. And so then in that case, when we have a fibration over an algebraic variety with a section, all of whose fibers are projective algebraic, then it is projective algebraic, say by a theorem of Campana. And this is, the X prime we get is obtained after an étale covering by first two deformations to a Jacobian fibration, and then to a fibration in abelian varieties. So, and this is projective. So I will stop my talk here because my time is over, right, Mohan? Is my time over?
Yeah.
Yes.